This video will review simple acceleration and distance equations, including the math and calculator knowledge necessary to work the problems. Before we begin, make sure you have whatever you're using as a calculator ready. I'm a huge fan of knowing how to do math by hand and practicing it regularly, but there are times you need to focus on other skills instead. It's important you know how to use your calculator correctly. Otherwise, you might understand the concept, do all the steps correctly, but still miss the problem because of a lack of knowledge about how to use a tool that's supposed to be helping you. So pause the video if you need to and grab a calculator, a phone, or whatever you're using to do arithmetic. We'll be covering two equations, acceleration and distance. Acceleration of an object is calculated by determining the change in velocity and dividing it by time. Note that change in velocity is final velocity minus initial velocity. This makes sense if you think about it. Suppose you and your friends started a We Love Math club at school. If you ask, how did our membership numbers do today? And he says, we have 8 more students. That means your final number would have been 8 larger than your initial number. For example, you started the day at 100 students and ended at 108 students. So 108 minus 100 equals 8. A negative number would mean the numbers went down. So if the next day 2 students quit the We Love Math Club, clearly this is a hypothetical situation, then you started the day at 108 and ended at 106. So 106 minus 108 was negative 2. Your change was negative 2. It makes sense that you take the final number minus the initial number, but it's so easy to put them down in the wrong order if you're not paying attention. So acceleration equals final velocity minus initial velocity, and that difference is divided by time. You might also see this written as delta V divided by t. Delta is a letter from the Greek alphabet and stands for change in, so that's change in velocity divided by time. In the second half of the video, we'll get to the distance equation. You might not have encountered the concept of squaring numbers much before, but don't worry, we'll get to that soon. First, we want to focus on the acceleration equation. Acceleration is the rate of change of an object's velocity. In other words, acceleration expresses how quickly or slowly an object's velocity is changing. To explain this, let's look at an example inspired from an event in my youth. I was walking our family's newly adopted greyhound, Holly. Up ahead, Holly saw a cat. It caught her attention, so she started speeding up. I thought it was cute, that was a mistake, and started speeding up with her. Random life lesson. It's a lot easier to stop a dog who is moving slowly than a dog who is moving quickly. That's momentum. So let's make up some numbers to represent my adventure. At the moment Holly saw the cat, let's say she and I were both traveling at 3 feet per second. She decides to speed up. Even for a greyhound, that's not instantaneous. It's a process. And I like to think she was somewhat aware of my existence at the other end of the leash, so she sped up slowly. Looking at the chart, you can see that for each second, the velocity grew from 3 to 4.5 to 6 until it reached 10.5 feet per second after 5 seconds. So the total change in velocity for the entire 5 seconds was 7.5 feet per second. That's 10.5 minus 3. But acceleration isn't just the change in velocity, but the rate at which the velocity changes. After all, if it took 5 minutes to reach the speed instead of 5 seconds, that's not nearly as impressive. So how fast was velocity changing? For each row in the table, compare the current velocity to the prior velocity. You can see that the velocity increased by 1.5 feet per second during each 1 second interval. A quick side note. Technically, I've only been speaking in terms of speed. Velocity is a vector and should also contain a direction. So for the purpose of this example, assume the direction is toward the cat. Directions don't always have to be north, south, east, or west. I think we were going to north, but it's been a few decades, so don't hold me to that. Now that you have the concept, let's use the equation. First, let's calculate acceleration during the first second. Just step through the equation and substitute the values one at a time. What's final velocity? That's the velocity at the end of the interval, which is 4.5 feet per second. What's initial velocity? Look at the beginning of your interval, 3 feet per second. How about time? Well, you started at 1:17 and 10 seconds and ended at 1:17 and 11 seconds, so that's 1 second. Now do the math. 4.5 minus 3 is 1.5 feet per second. 1.5 divided by 1 is 1.5. So that's a change of 1.5 feet per second for every second. 1.5 feet per second is the same as 1.5 feet per second squared. I'll explain that in just a minute, but I want to use our equation for one more interval first. Let's do the interval from 11 to 15 seconds. Same process as before. Final velocity, 10.5 feet per second. Initial velocity, 4.5 feet per second. Time elapsed, we started at 11 and ended at 15. Just like change in velocity, change in time is final minus initial. So 15 minus 11 equals 4 seconds. Now perform the arithmetic. 10.5 minus 4.5 equals an increase in velocity of 6 feet per second. 15 minus 11 equals 4 seconds. Notice that the change in velocity here, 6 feet per second, is much larger than the 1.5 feet per second in our first calculation. But we don't want change in velocity, we want the rate of the change in velocity. Since that 6 feet per second increase in velocity was spread out over 4 seconds, the rate of change is 6 divided by 4, which is 1.5 feet per second increase in velocity for each second. So again, we get 1.5 feet per second, or 1.5 feet per second squared. You might be wondering how a measurement in feet per second divided by a measurement in seconds gives us a measurement in feet per second squared. So let me show you, explaining first with regular numbers instead of units. When you have a fraction, a over b, and you divide it by c, that fraction can also be represented as a over b times c. So both the b in the denominator of the original fraction and the c that you then divide the fraction by can be multiplied and be put in the denominator of the new fraction. With regular numbers, let me show you. If you had 1/5 and you divided by 4, you could also express that as 1 over 5 times 4, or 1 over 20. Visually, you can see it as this. Here is one rectangle. I'm going to take my rectangle and divide it into 5 equal pieces. So 1 would be 1/5. Then I'm going to divide that piece, and I'm going to go ahead and divide all the others at the same time, into 4 equal pieces. So one new smaller piece would be 1/20th, because as you can see, my original one rectangle is divided into 20 equal pieces. So when I took 1/5 and I divided it into 4 pieces, I got 1/20th. Units work the same way. If I have feet per second, and then I divide by seconds, I can have both the second from the feet per second and the second I divided by in the denominator of my new fraction. And that's feet over seconds times seconds, which is feet per second squared. Again, if the squared is confusing you, hang on, we're about to get to that. If you're using a scientific or a graphing calculator, you might find that you don't always get the answer in the format you were expecting it in. For example, if you typed in 1 divided by 2, that's equal not only to 1/2, but it's equal to 0.5. And depending on the situation, you might want one or the other. And with a more complicated number, it wouldn't be easy for you to figure out in your head. So if you have a fraction and you'd rather have a decimal, or if you have a decimal and you'd rather have a fraction, look for this button or something similar, an S to D button, and that'll help you go between the fraction and the decimal answer. All right, grab your calculator and figure this out for me. What is 5 plus 10 over 10 plus 5? Now, a lot of people, when they type it in to their calculator, they're going to type it like this. You would expect the answer to be 1 because 5 plus 10 is 15 and 10 plus 5 is 15. So 15 divided by 15 should be 1. But if you type it in like this, you're going to get 11 as your answer. What's going on is a problem with order of operations, so let's get into that a little bit. Order of operations is what tells you what order to perform calculations in when you have a complicated expression. You also hear this referred to as PEMDAS, or the memory device, please excuse my dear Aunt Sally. The order of operations, number 1 is parentheses, that's your P. Number 2 is exponents, that's your E. Number 3 is multiplication and division, that's your M and your D, they go together. And number 4 is also a group, it's addition and subtraction. As an example, if you were evaluating this expression, the first thing you'd look for is parentheses. If you have parentheses, which we do, you perform that calculation first. 9 plus 1 is 10. So now you can put that in. There's no more parentheses left, so now what do you look for? You look for exponents. We have an exponent here, so we figure out what 3 squared is. That's 9. We put that in there. Now it's time to move on again. We've done all parentheses, we've done exponents, so now we look for multiplication and division. We have 2 instances, and so we work from left to right. 60 divided by 10 is 6. 2 times 5 is 10. So we take that and we continue to simplify our expression. And now we're just down to addition and subtraction. Again, you can work from left to right, and we have 7 plus 9 minus 6 plus 10. We figure that out, and it's 20 is our answer. So what does the order of operations have to do with us not getting the right answer for our fraction? A lot of people don't realize this, but when you have a fraction, there are implied parentheses around the entire numerator, that's the top, and the entire denominator, the bottom. When we typed the fraction into our calculator as a division problem, it was no longer in fraction form, so there were no longer implied parentheses. So here, according to order of operations, the highest rank you have is division. You do 10 divided by 10 and you get 1. That leaves you with 5 plus 1 plus 5, which explains why your calculator thinks the answer is 11. So how do you evaluate fractions with a calculator without getting it wrong? You have some choices. Number 1, use parentheses. If you've got a scientific or a graphing calculator, you'll have buttons like these. And just put those parentheses around what would be the numerator and denominator of your fraction and have the divided sign in between. You'll get the right answer. Number 2, use the fraction button. A lot of calculators have this. It might look something like this. You use that button. You can use the arrow keys to go between the 2 boxes and type what you need in each box. You should get the right answer. Finally, maybe you're not comfortable with these, or maybe you don't have a calculator that has these. Break it into steps. Figure out what 5 plus 10 is. It's 15. Write that down. Figure out what 10 plus 5 is. That's also 15. Write that down. So now you use your calculator to figure out the top and the bottom, but on your paper you've written down the answer to each step. Now you can go in and type 15 divided by 15 in your calculator and get the answer as 1. Take a moment to make sure you know how to use your calculator. Evaluate the expression 5 plus 10 over 10 plus 5. And whichever method you prefer, make sure you can get the right answer for that. Let's use the physics, math, and calculator hints we just learned to solve a word problem. A car is traveling 45 feet per second to the south when the driver sees a turtle herd crossing the street ahead. Slamming on the brakes allows the driver to come to a stop in 7.5 seconds. What was the driver's acceleration? Now, I do believe we should use the term turtle bail from what I've read, but I just like saying turtle herd, so I'm going to stick with that. First, when solving this problem, ask yourself, what do I know? What does the problem tell me? Velocity is 45 feet per second to the south. Time is 7.5 seconds. Next, what does the problem want you to find out? Acceleration. Great. Now, what equations and helpful facts do you know? Well, we have this nifty little acceleration equation. Final velocity minus initial velocity over time. So now you're ready to fill in the values and solve. Get your equation. Remember, what is it you want to find out? That's acceleration. That's right here. So that equation can help us. We need time. We have time. Looks good so far. But now we run into a problem. We need final velocity and we need initial velocity, but we only recorded one velocity in our problem. We need to read the problem a little more carefully. So we're just going to go back and add to it. What we realize is if we're coming to a stop, that means our final velocity is 0, and the 45 feet per second must be our initial velocity. So now that we have that, we can plug everything into our equation. 0 feet per second for the final velocity, 45 feet per second for initial velocity, 7.5 seconds for the time. 0 minus 45 is negative 45. Negative 45 over 7.5 is negative 6. So negative 6 feet per second, or negative 6 feet per second squared. And what does that mean, a negative number? That means the car's velocity is decreasing, or we call it decelerating. 6 feet per second for every second. Now we're ready for that second equation, the distance equation. Distance traveled while an object is accelerating for a given amount of time is equal to 1/2 multiplied by acceleration multiplied by time squared. There are a couple restrictions on when you can use this equation. First of all, acceleration needs to be constant. If the acceleration is changing, then you don't know what number to plug into this equation. Also, initial velocity must be 0. So whatever object you have has to be starting from a stop for you to be able to use this equation. Note that it's not time in this equation, but time squared, denoted by that small raised 2. When a number has a smaller number written above the line, we call that a superscript. When a number has a smaller number written below the line, we call that a subscript. When that superscript is a 2, that's when we're dealing with squared numbers. Squaring numbers is actually quite simple. When a number is squared, that just means you multiply it by itself. 5 squared would be 5 times 5, which is equal to 25. 21 squared would be 21 times 21, which is equal to 441. You can square integers, you can square fractions, you can square decimals, you can square negative numbers. Take any number, multiply it by itself, and that's squaring. Grab your calculator and make sure that you can square a number by using some of these examples to check yourself. For a scientific or graphing calculator, there should be a button that quickly squares numbers for you. Look for a button similar to this, with X or A or some other letter as the base and a superscripted 2. To use this feature, type in the number you want to square. Then press the X squared button and it will fill in the superscripted 2 for you. Then press equals or enter to get your answer. Please note that when squaring fractions on your calculator, you need to be careful to square the entire fraction. Typing in the fraction and hitting the X squared button will only square the denominator. You can use parentheses around the fraction so the exponent applies to the whole fraction. Or you can type in your fraction as a division problem and hit equals or enter. Then use the answer key to bring up your answer and apply the X squared button to the answer. Most calculators will actually let you skip the step of hitting the answer key. If you hit an operation key instead of a number immediately after hitting equals, they'll assume you're applying that operation to the answer you just got. If you have a basic calculator, that means it doesn't do much more besides add, subtract, multiply, and divide. Just type your number, multiply it by itself, and hit equals. You should get the answer. If you have a large number or a long decimal that is troublesome to type in twice, you can use the memory buttons if your calculator has those. First, clear the memory with memory clear so the running total is reset to 0. Then, type in the number once and add it to your memory with the memory plus button. Now it is saved in memory. To calculate the square of that number, press memory recall to get the number, times memory recall to get the number again, equals, and you should get your squared number. If you're using a smartphone as a calculator and only have basic functions, try turning your phone sideways, landscape mode. So some phones will switch to a scientific calculator when the phone is turned. If not, there are plenty of apps out there you can download with a parent's permission if you want more than just basic calculator functions. Before we move on from exponents, squaring numbers is only a small subset of what exponents can do. Like we said, x squared, a superscripted 2, means x times x. Y cubed, a superscripted 3, is y times y times y. There are 3 y's. You could take z to the 4th power. There'd be 4 z's, z times z times z times z. Similarly, theta to the 5th power would be 5 thetas all multiplied together. So test your calculator. 5 squared is 5 times 5, 25. 7 cubed, 7 times 7 times 7 is 343. Make sure you can get the right answers. When you want to do exponents on a scientific or graphing calculator, look for the x to the y button or x to the blank button. On your calculator, hit that button and it'll give you something that looks like this: a full-size square and a smaller superscripted square. Use the arrow keys to go inside each rectangle and fill in the number you want to have. Hit enter or equals and you'll get your answer. You can also go ahead and type in the first number, the base. Then when you hit the x to the y button, it will just leave you a blank spot for filling in the exponent. Fill that in, hit enter or equals, and you get 343 or whatever answer you're looking for. Let's wrap everything up with a word problem using the distance equation. A ball is sitting at the top of a hill when a slight gust of wind causes it to start rolling. The ball accelerates 0.5 feet per second per second. How far has the ball rolled after 6 seconds? First, ask yourself what you know from the problem. Time equals 6 seconds. Acceleration equals 0.5 feet per second, or 0.5 feet per second squared. What does the problem want you to find? Distance. How far has the ball rolled? What equations and helpful facts do you know? Distance equals 1/2 times acceleration times time squared. Also remember, initial velocity must be 0, and the ball starts sitting at the hill when the wind just sort of nudges it just enough so it can start rolling. So initial velocity is 0. Let's fill in our values and solve. We'll start with our equation. The problem wants us to find distance, and this equation has distance, so it looks like a good choice. We need acceleration, we have acceleration. We need time, and we have time. So let's plug everything in. We put in 0.5 for the acceleration and 6 for the time. Distance equals 1/2 times 0.5 feet per second squared times 6 seconds squared. Now notice when you square the 6 seconds, you square the 6 and you square the units. So 6 seconds squared becomes 36 seconds squared. All right. Those cancel out, the second squared and on the bottom of the acceleration and the second squared that came from our time squared. So what we're left with is 1/2 times 0.5 feet times 36, and that equals 9 feet.